Yeah, hello everybody. My name is Jan Zimmermann. I'm one of the two general managers at TEWS, together with Tim TEWS sitting right there. And I'm going to give you a short, brief technical overview about the VITA 93, also known as QMC. So first of all, we'll handle the physicals of the QMC, which is first of all the size. You can see here the single QMC with the sizes of 26 millimeters times 78.25 millimeters, which is, compared to XMC or PMC, really small. But I think with a shrinking IC package sizes, it's rather the perfect match. Also, the small size allows us to build single function modules. So if the carrier provides enough QMC sites, the system integrators can just add more and more functionality by just adding in one of these small cards. Also, the component height, the 4.7 millimeters, is well known from, for example, PMC and XMC, and has proven sufficient for most circuit designs. Then we have the connector that we use. It's actually capable of PCIe Gen6 with an up to X16 link. And another thing that is really important with QMC is that you may want to supervise the module's health via IPMI. And the QMC offers a great approach to be seamlessly integrated into managed systems. So that means it can be supervised and managed, but it does not have to. Then regarding the IOs, a single QMC comes with 40 IOs for the single. So for that module size, it's a really high IO density. But it's not only the IO density, it's also the IO speed that is special about it. And that especially allows its use with high-speed interfaces like, for example, Ethernet or Vision. Next up, I want to talk a little bit about the scalability that Mark already mentioned and why scalability is so important. You can see here we have a single, double, triple, and quad QMC, and it just scales up in size, which we've shown here. And the scalability allows us to use the QMC for a whole range of application, starting from simple I/O functionality on a single QMC up to highest complexity solutions with, for example, a quad QMC when you, for example, use a Zinc UltraScale as a system on module. So the QMC designers can adjust the size of the QMC according to the functionality they need or want to implement. So on a quad viewer design, for example, would fit perfectly on a single size QMC, while a large system on chip from example, AMD or Intel would definitely need more. And what does it need more? It does need more PCB area, more power, more connectivity, and also more I/O. And to address these demands, the QMC grow not only in size, but also in power, connectivity, bandwidth, and I/O count, as you can see on the slides. Also, the carriers can be populated with different combinations of the QMCs. So you can put a single QMC and a triple QMC on a 4-site or 4-slot carrier. And that is only limited by the PCIe link and the QMC sites on the carrier. Next up, we're going to talk about the host interface. You see the PCIe connector, so the host connector for the QMC is on the right. And it basically provides everything the QMC needs. First of all, you need power. It offers 3.3 volt for low power designs. And for high power designs, you would go for the 12 volts and maybe also the 3.3 volts in parallel if you want to save some space on the PCB for the onboard power supplies. And secondly, you need, of course, connectivity. And here the QMC's only interface standard is PCI Express. That may seem a little limiting at first, but actually it ensures interoperability because this way, as Mark already said, every QMC will fit on every carrier. So also a single QMC, as shown in the previous slide, has the capability of using PCIe X4, and that scales up to PCIe X16 for a quad QMC. And then, as a third point, you may need to supervise your QMC via IPMI, and that is definitely possible with QMC, but we've dedicated the whole slide to that, so more about that later. And then, as a last thing for this slide, we have the JTAG interface that allows thoroughly testing and factory programming of the QMC without wasting valuable PCB space for example, debug headers or an onboard test. Then we have the I/O connector and the I/O capabilities of the QMC. You see it's the same 80-pin connector type as you already saw with a host connector. And it provides 20 differential pairs per single QMC, which can also be used as 40 single-end I/O signals. And in addition to that, every I/O pin has its own ground pin, which is critical for the signal integrity of high-speed interfaces. Then the I/Os are grouped or organized in I/O pipes, 5 to be exact, as you can see here. This is an I/O pipe, and you have 5 on those on the connector. And they provide structure during design and usage of the QMC. Each I/O pipe consists out of 4 differential pairs and their individual grounds. So this means each I/O pipe has its own ground reference plane. And this allows us to support also isolated interfaces like, for example, 10G Ethernet. And it's really a large improvement for the system. And then once again, you see here the QMC's I/Os, they scale up to 160 per quad QMC. So regarding the cooling concept, we'll handle air-cooled and conduction-cooled real quick. What you can see here is an air-cooled QMC on an air-cooled carrier. And the mechanical fixation concept of a QMC follows a very simple rule, and that is that the carrier provides all mounting hardware. On the one hand, that means that the whole or complete mounting kit has to be provided by the carrier. This includes the screws, spacers, and on the other hand, that frees up the QMC designer from worrying too much about mechanical stuff, and also the integrator from compatibility issues. The standoffs you can see here, they're already pre-mounted on the QMC carrier, allowing us the easy mounting with the screws and the spacers of the QMC on the carrier. And the spacers, these ones, they're needed because to cover the place for a potential heatsink of the QMC, because the QMC specification allows us to put a conduction-cooled QMC module on an air-cooled carrier. Next up, we have the conduction-cooled version. Here's an example of how that may look like on the right, where you have the carrier on the bottom and the QMC on top, together with the Skyline heatsink, which is the only mechanical part that comes with the QMC and is usually pre-mounted. Then, once again, as with all the other QMCs, all the mounting hardware comes with the carrier. This includes spacers, screws, the thermal interface material that you see here, and of course the heatsink for the conduction-cooled carrier. So that means that the design of the cooling structure is 100% up to the carrier designer, as long as the mechanical envelopes are not violated. Also, this again ensures interoperability. One thing I want to mention in particular here is the thermal interface material here in red, because it extends over the whole QMC and provides a direct high-performance thermal interface to dissipate the QMC's heat. And that is really important and critical because of the amount of power dissipation you will need for QMCs, and also a great advantage over traditional mezzanine concepts. But more towards the power budget later. Last but not least, we have the stacking heights, where you all know traditional mezzanine cards come with a fixed stacking height, often forced by the fact that the mezzanine provides the mounting hardware, and that works really well for systems that match the fixed stacking height, but is a kind of a drawback for systems that would allow more stacking height. That's why QMC comes with a variable stacking height of 9, 11, 14, and 16 millimeters. The variable stacking height maximizes the component envelope of the carrier, for example, for CPUs or single board computers, resulting in additional space on the carrier. With that said, the QMC itself will always stay the same, and that means it will always fit onto every carrier independent of the stacking height of the carrier. And consistent with a policy that all the mounting hardware needs to be provided by the carrier manufacturer, also the carrier will define the stacking height of the QMC.